All right, so that I don't forget. And share screen. All right, so let's go ahead and get started. New topic today. We're gonna do weak form in 2D. So a little bit of math very similar to what we did for 1D, but we need to recap a little bit on calculus, vector calculus. So instead of single scalar or single variable calculus, vector calculus. This is just to give you a little bit before I get started, to give you a little bit of an idea of what we're going to do in this. This is kind of the second part of the course. There's 3 chunks in the course. The first one was doing everything in 1D. We started with the trusses. That was just a tiny little bit just to show the assembly process, getting the system of equations, and then solving that with Python. But that was really only maybe 2 weeks, and then, or not even 2 weeks, but yeah, about 2 weeks. And then we went all in for the FE with a PDE in 1D, strong form to weak form, finite element discretization, put those 2 things together, get a system of equations. And that is sort of the combination of that is the Python Lab 3 that I uploaded last week, and your homework, what is it, 3? Your homework 3, and the exam, the first exam. So all of that sort of wraps up basically the entire, all the concepts, but just in 1D. So it covers the math of the strong form to weak form. It covers the math of the interpolation using the finite elements, and how you put those 2 things together to get a system of equations that you can solve. Now, in this second part of the course, it's going to be exactly the same. So repetition of those 3 steps, but in 2D. And then for the very last end of the course, we'll do a little bit of elasticity. The reason why I do that in sort of a middle part and an end part is that for what we're going to do in the second part is still a scalar problem. So it's a problem in 2D, but it is a scalar problem, which is the heat transfer, meaning that the unknown is a single number, or a field, but it's not a vector field. So when you do elasticity, when you solve for the stress, you have done that in the Abacus lab. You don't get a single value of stress, you get a matrix for every point, right? And so because of that, setting up that problem is a little bit more difficult. Whereas what we're gonna do here is more like the lab that you did, lab 4, which is the heat transfer problem. Your unknown is a single scalar, is the temperature field. So that one is a little bit easier to set up. So for 2D, we're gonna do first the scalar problem, the heat transfer problem. And then at the very end, we'll do a little bit of elasticity, just because adding in complexity. All right, so before we get started to the strong form to weak form, I just need to remind you of a couple of things that just notation and remind you of the vector calculus. One thing that we're going to have in 2D is we're going to have a domain. And I've always referred to, even in 1D, I refer to the domain as omega. But in 1D, omega was just a part of the real line. It was just x from some initial x to some final x. Now, omega is some portion of the plane. And that domain has a boundary that we're gonna call, so boundary we're gonna call, this is the domain. And the boundary, just by notation, we're gonna call either partial omega or gamma. I've also used gamma in 1D. Now the gamma in 1D is basically just the beginning and the end of the line. But in 2D, it's basically a curve in the plane. Yes, so points in the domain. So points in the domain, we're gonna denote with x. I'm gonna use this x underscore to denote the vector. So these are points on the domain are vectors. Again, just as opposed to before where I just had x, the variable x, now it's a vector. So that means that obviously you can express it as some x component and some y component. So if you are familiar with your IJ notation, so it has components. Then we are interested in functions, just like before. Here we name them a little bit different. So functions over omega are called fields. Just a fancy word for function. And then there's different types of functions. So there can be scalar functions, like the temperature. And I'll illustrate that in a little bit. There's vector or scalar field. I should say scalar fields. If I say that they should be called fields, I should say scalar fields. Vector fields, for example, a displacement field. Note that if it's a displacement field, which is a vector, it will have components. So this u of x, you will be able to express as ux plus uy. And there's something called tensor fields. And tensor is another just fancy word. It's not just fancy, it has a reason why it's not called a matrix, but this is essentially a matrix. You can think of this as a matrix. It's not exactly a matrix, but. And that includes, for example, the stress field. And that, I mean, the reason that the elasticity problem works with the stress field, and that one is this tensor field. So that's why we leave that for the last part of the course. Yeah, so for the scalar problem, actually, all we need is these two. All we need to know is what a scalar field looks like and what a vector field looks like. Let me illustrate that, for example, for the temperature field. A temperature field means that you can get a contour plot. That's pretty much all you need. So if you have some you have your domain X, and you can basically assign to every point, and that's the just adding some coloring with Adrian. So this is an example of a scalar field you can represent as a contour, right? So temperature field contour plot, or I would say in layman's terms, people refer to also as a heat map. Not surprisingly, because it's associated with, I mean, people refer to it as a heat map, not just talking about a heat transfer problem, but in general. And this means that for every point, any point here, you basically, so for any point X, there is a temperature And it just so happens that I can color, higher temperatures or lower temperatures with a different color. And so temperature is a single value, but it is a function over x. So it's a scalar valued function of an x domain, vector x. Takes in a vector, but spits out a number. Whereas the vector field, typically, you represent a vector field with what would be called a quiver plot. You can do this in MATLAB or in Python as well. And basically, for every point x, you get a vector. Right, so for every point, for every x, there is an associated u. No good way of representing the tensor field because matrices is difficult to paint them. Anyways, so these are clearly functions because or fields, because for every point x, you can evaluate either this vector field or this temperature field. All right, so that is some notation, and then gradient and divergence operator. So maybe I'll add one page here. So what is gradient and divergence? The gradient operator is like a derivative, but in 2D, it's denoted with this operator called nabla operator. And it's associated with some derivative. Associated with differentiation. And it's such that it raises from scalar. So the gradient of a scalar field will be a vector field. The gradient of a vector field will be a tensor field. What does it look like in particular? So what is the gradient of t? Let's define that as q. So it's going to be a vector field. And it's going to be a vector field made out of the partial derivative of t with respect to x and the partial derivative of t with respect to y. I can do one example in a little bit. That is the gradient of scalar field gives you a vector field, I should say scalar vector. So for the gradient of u, that is, for example, almost epsilon is not quite epsilon. I'm gonna call it E. It's not quite the strain. Actually, how should I call it? Let me call it F just for. So this one is gonna be a tensor, which means kind of a matrix. And this is gonna be the partial of ux with respect to x, the partial of uy with respect to, sorry, here it should be still ux, but with respect to y, partial of uy with respect to x, partial of uy with respect to y. And I can make the dependence explicitly. Note that this ux is a function of both x and y. So it's a function of the x vector. That's why we can take partials with respect to either x or y. So that's the definition of the gradient. We'll do an example. But yes, question.
So the first one, is that a lowercase q?
Yeah, lowercase q. What does it look like? So I don't know what it looks like, but it is a lowercase q. Because typically you will see the gradient of the temperature is associated with the flux. It's not quite the gradient of it's minus the gradient of the temperature times something, but Q and F. All right, so that defines the gradient, and let's define the divergence. The divergence typically is with the nabla operator and a dot product. So it's nabla plus a dot product. It is also associated with differentiation because there's a nabla involved. But it will reduce the order of the field. So for that one, if you have a vector field, so let's say that you want to do the divergence of a vector field, will give you a scalar. And the divergence of a tensor field will give you a vector field. So the gradient sort of raises the order of the field from a scalar to a vector, from a vector to a tensor. The divergence also involves some derivatives, but it lowers the order of the tensor field. So from a tensor to a vector, from a vector to a scalar. What does it look like? So if I want the divergence of Q, that one is going to be a scalar, and it's going to be the derivative of x with respect to x plus the derivative of the second component with respect to y. So this is a scalar. It takes in the two components of Q. So Q is a vector and has an x component and a y component, and the divergence is a scalar. It does use the both components, but it adds them up. So you can see that this is similar to a dot product, right? So when you do dot product of two vectors, you multiply their x components and add them to the multiplication of the y components, and the result is a scalar, right? So if you have two vectors and you do dot product, you get a scalar. You can see kind of maybe where this comes from. So the gradient, which has a partial x and a partial y, and you dot it with a vector, then you kind of multiply the x component of the gradient, which is partial with respect to x, with the x component of the vector, which is the qx, and then you add up to the second part of the dot product, which is the partial y with the qy. So it is kind of a dot product of the gradient operator with the q. For the gradient of a vector of a tensor field, sorry, the divergence of a tensor field, that one will give you a vector. So in this case, a 2x2 matrix will result in a 2x1 vector, and it will involve partials. So this will involve the x component, bless you, with respect to x plus the xy component with respect to y. And here the yx component with respect to x plus the yy component with respect to y. Just to know what XX is, this will be the XX entry, the XY entry, the YX entry, the YY entry. So note that this is a vector, right? So I mean, it has the same 4 components, but you can see that it's just 2 lines. It's a vector with 2 components. Any questions? One last thing, I mean, they typically don't have, especially when you go to tensor fields, there's no interpretation, but they do have, for the scalar and the vector case, they do have an interpretation. You probably know this. So what is the gradient of a field, of a scalar field? So if I have, I think you will know this. Let's see. So if I have this, I think I would fail in my kindergarten for staying inside of the shape. My little colorful egg. If I ask you to draw, this is the temperature field. What is the gradient of T? This you probably know, hopefully. It's not necessarily the flux. The flux is going to be related to this, but before getting to the flux, if you were to draw the arrows corresponding to the, this is a, I shouldn't have called it flux because the flux is minus the gradient, but actually let me call it a little bit different. Let me call it V, just to not name it the flux yet. If you were, so this is a vector field, right? So this is a scalar field, which I have the heat map there. This is a vector field, so it should be associated with a quiver plot, so a bunch of arrows. How should I draw the arrows corresponding to that V? Exactly. They point in the, basically, and they should be orthogonal to these contour lines. So they should point, basically, they should follow the direction of maximum increase of the field. So B should point in the direction of max increase of T. So in particular, they should be orthogonal to these contour lines. And so the flux is actually, maybe I shouldn't have used Q before. The flux is minus that. So the flux is always in the direction of the negative of the gradient of the temperature. Which is just exactly the same, just flip all the arrows, and that's where the flux should go. So it does have a physical interpretation for the gradient, at least the gradient of a scalar field. I don't really have a good way of explaining what the gradient of a vector field is. We just don't have very good intuition with matrices. But for the scalar field, the gradient of the scalar field is that quiver plot, which is the direction of maximum ascent. Gradient of scalar field. That's one that has an interpretation. The other one that has an interpretation is the divergence of a vector field. That one also has a meaning. And so this is vector, and it gives you a scalar, which I'm going to name S. And for that, I'm just going to draw a little box here. And so Q, if Q is sort of the vector field associated with Q, the vector field associated with some flux, if you take the divergence of that vector field at some small patch, that will give you a scalar. So it's like small, let me call this small patch. That will give you some scalar. Imagine that you repeat this for every. So this will give you a scalar. That S is basically the amount of stuff that I either gain or lose in that little patch. Not that loose, the loose with a single. So typically this would be called a source term. So if you take the divergence of Q, essentially what you are doing when you're doing the divergence of Q is you are calculating how much flux you get in from the different directions. And then you are adding that up to get the total amount of stuff that you either gain or lose by knowing, how much you got in, how much went out. In fluids, you might have done. Did you see this in fluids? What is the divergence of the velocity field for a fluid? You never use this? This is called the continuity equation in fluids, no? No? Divergence of velocity? 0. So if this if it's incompressible. This means if you count basically all the particles that go in and out of a small region, then mass should be conserved. So therefore the net loss or gain of mass should be 0. At least for incompressible. But that is the meaning of the divergence. So if you have the divergence of a flux, that tells you basically the local gain or loss of that, whatever is fluxing. So if it's, if it's heat, then the divergence of the heat flux tells you how much heat you gain or loss at a point or at a small patch. it has an interpretation. It's difficult if I give you just the entire vector field. It's difficult to know, but it has an interpretation. Okay, so I have those two. All right. So then the next thing, which is in the book, is Green's theorem. Is basically integration by parts. But this is not integration by parts. Green's formula is integration by parts. So what is Green's theorem? Is a way of, you probably did this for your vector calculus class, is a way of relating integrals over the domain to integrals over the boundary. And basically what you see there is that the integral of the gradient of a scalar field is the same. I'm not gonna do any proofs or anything, but you can see that this is an integral over omega. So that means that if I have a scalar field, for example, the temperature, theta, I take the gradient, I get some quiver plot, right? So this is the gradient of theta. If I integrate that vector field over omega, I will get some vector. And that is the same as integrating the value of the theta and at the boundary times the normal. I'm really not gonna derive this, but just main thing here is that there's a relationship between taking integrals over a domain and integrals over the boundary, and there is either the divergence or the gradient involved. Super non-intuitive, but super powerful. Because it really doesn't make any sense, right? You have some field, you take the gradient, and then you integrate that, and that is the same as integrating the field over the boundary. But it is. So that's one thing. Again, I don't need you to know much about it, except that it exists and it relates integrals over the domain to integrals of the boundary, and there's some gradient or divergence involved. There's the divergence theorem, which is similar. So these two are very complementary to each other. In this case, you have a vector field, which is like a flux. This one actually does have more intuitive meaning. So this one says that if you take the divergence of that vector field and then you integrate it over the domain, that is the same as integrating the Q over the boundary. So this is Q dot N, gives you some scalar. This one actually has an interpretation. This is sort of the scaled up version of what I was explaining for the divergence. So this one is that if you have some, now it can be a bigger patch, but you can do it with let's say I have some square and I have some Q in at the left boundary. Let me call this left. I have some Q out in this other part of the boundary that I'm gonna call just this one part of the boundary. This is another part of the boundary. Let me call this one gamma out. And let's say that there's no flux in the other two boundaries. So Q equals 0 on, let me call it gamma no flux, both of these. So if I tell you how much stuff I have in my box, I think you would intuitively integrate the amount of flux that goes in and out of the boundaries. So you would intuitively do this one, right? So if I ask you how much stuff do I have in my box, you would do that. you will integrate basically all the fluxes over the boundary. And what I told you about the divergence is sort of local gain or loss of stuff. So what is the equivalent of integrating over the entire boundary? The flux is integrating over the domain. So then obviously the Q is still defined also inside, right? And what I told you is that for every point here, or for every small region, if you take the divergence of the vector field, you get basically the local gain or loss of that stuff. So if you take, so divergence of Q at that point is local gain or loss of stuff. So if the divergence of Q at a point gives you the local gain or loss of that stuff, then if you want to know how much in total you gain or loss, then just integrate the divergence of Q over omega. So this is basically total gain or loss by integrating the local gain or loss over the domain. Whereas this one is total gain or loss by integrating fluxes over boundary. So this one actually has some more intuitive meaning. Any questions? It's a lot of recap of your calculus, vector calculus class. That's it. So there's Green's theorem, there's divergence theorem, and then out of this you can derive, and this is in the book, by the way, out of this you can derive, this should not be called Green's theorem, this is called Green's formula. This is basically the integration by parts in any dimension, actually. This works for 2D or 3D. So hopefully you see that this has more or less the same structure as the integration by parts formula that we use in 1D. This is sort of your A. This is sort of your dB. So you have an integral over omega of A dB, and that one we can turn into an integral over the boundary of A times B. So you can see that you have sort of A and B. There's a normal involved because of this divergence theorem and Green's formula that I was showing before. But it looks kind of like that, right? So you have W times some derivative of Q, or divergence of Q. And then we are basically passing in the boundary, we get rid of that derivative. We still have the dot product, and that dot product ends up with the normal. But we got rid of the derivative and minus the integral over omega of, and you can see that we sort of passed the derivative. So now this is dA and this is B. I don't want you to learn the derivation, but this is what we're gonna use for transforming the strong form to the weak form. But hopefully you see the similarities between this and integration by parts in 1D. We basically just took that nabla and sort of passed it to the W, and then we end up with this extra integral over the boundary of AB. All right, so with that, we can actually do this I'm not going to do the derivation, but what is the strong form? All of this just to show you what the strong form to weak form for the heat transfer problem is. In 2D, the energy balance, PDE, is the divergence of the flux, of the heat flux, equals the source, or if you put the source on the left-hand side, is the divergence of the heat minus the source should be equal to 0. And that is over omega, where the flux is actually related to the unknown. What I want to find is actually find T. I want to find the temperature field such that I satisfy my energy balance equation. Obviously, this goes right there, where the heat flux is minus the gradient of the temperature scaled by some conductivity with either natural or essential boundary conditions. Natural boundary conditions means I know the flux. Essential boundary conditions means I know the temperature. So you can see that this is a PDE because that gradient or that divergence involves some derivatives. So we'll do the weak form. So how do we do the weak form in 1D? We multiply by a weight function and integrate. Multiply by W of X and integrate. So we have divergence of Q minus S times W integral over omega equals 0. So again, I just took the PDE, multiplied by a weight function, integrate over omega. Exact same step that we did in 1D. What is the second step? When you do it in 1D, what do you do? You do integration by parts, right? So we're gonna do integration by parts. Well, I may put it in quotation. Yes, integration by parts. In this case, basically Green's formula. So if you go back to the previous slide, I'm gonna rearrange this a little bit so that it looks like the formula that I have above. This S can be a function, so I'm just gonna put it as a function. So the integration by parts, we only need to do it for the term with the second derivative. It doesn't look like there's a second derivative, but there's a second derivative here. I would say here, there's a hidden second derivative. Why? Because the Q already has one derivative, because the Q is the gradient or minus the gradient of the temperature. So there's one derivative there, and there's another derivative with the divergence. So there's another derivative. So if you use Green's formula, you just go back to what I had before. You get an integral over the boundary of the W times Qn over the boundary. So this is an integral over the boundary minus an integral over omega of, I'm gonna pass that gradient to the W. So we're gonna end up with gradient of W dotted with Q. And that is an integral over omega. And then nothing happens to the other term. So to the other term just stays the same. So you can see that we pass the derivative from the Q to the W. So instead of having divergence of Q times W, now we have you have gradient of W times or W with Q. And then we get this extra integral over the boundary. All right, what is the, oh, do I still have space? Yes. So what is the third step? So after doing integration by parts, what do we do? In 1D, what do you do? Boundary conditions, yes. So what exactly were the boundary conditions? We did something for the W and what did we say in 1D? Yeah, for the boundary conditions. So what happens when we have essential boundary conditions?
You set the okay function to 0.
Yes, so if I know T on part of the boundary, then immediately in that part of the boundary, W equals 0 on that part on that boundary. And otherwise, I should know, or I know the flux. Some whatever flux, let me call it Q star. Substitute. So just to remind, I have 3 minutes. I will barely have time to finish this. But you know, there's part of the boundary where I know the temperature. So let's say that this is the part of the boundary. So in this part of the boundary, I know the temperature. Let's say that I know that here T equals T star. That part of that boundary, I'm gonna call gamma T. And there's other part of the boundary where I know the flux. That boundary I'm gonna call gamma Q. And similar to the 1D problems, if you don't know a specific flux, then you actually do know the flux and it's just 0. So in this case, I only drew some arrows in some part of the boundary. But if I am not given any information, that means that I actually know the flux is just 0 in the other parts of the boundary. But you know either or, either you know the flux or you know the temperature. Okay, so that means that in this part of the boundary, so W equals 0 on gamma T. So what that means is that if I go back to my weak form, so that means that this, I only need to care about the one where I have the and only the normal component of the flux matters. So here, so W equals 0 on gamma T, so I don't need that part of the integral. And then Q equals Q star on gamma Q. And that's it. So the problem is find the temperature such that the temperature equals T star on, so essential boundary condition on gamma T, and equation 1 is satisfied for all W with W on W of X on gamma T equals 0. So Wx equals 0 on gamma T. And that's it. So this is the weak form. All right, let's stop right here. And then I'll see you on Friday.
Ready.